Howdy folks, this is Mr. Wood coming to you, I was going to say live from here in room 336, but pre-recorded. So anyway, you're working right now on problem number 57, where you're asked to find if momentum seems to be conserved. At least this is the first part of number 57. And no, I think is probably what most of you have come up with, or at least that's what I'm hoping, that it seems like momentum has not been conserved. This was a problem that presented itself to folks such as Wolfgang Pauli back in the early 1930s. And so when he saw this beta decay, this neutron decaying, um, it looked like that momentum was not conserved. The neutron just sitting here originally has no momentum. And so when it decays and things shoot off from it, the after effects should have as well no momentum, or at least that's the idea going into this. But it turned out that it looked like that there was a net momentum going off in a particular direction. The proton and the electron could be accounted for, but not the rest of the momentum. And it was this idea of conservation of momentum was so strongly believed that they came up with this idea of the neutrino and a little neutral one, as it's called, a neutral particle that has very little mass and that apparently would be undetected. And so this was hypothesized at the time as something else. And indeed, 20 years later, this was verified, the existence of neutrinos. And now today we understand neutrinos to be part of the standard model of particle physics. Right here, they're the part of the lepton group here. There are three types, and these neutrinos are again being buggers in the scientific community. These are the particles that have been supposedly measured to be going faster than the speed of light. So they challenged us back in the 1930s. They still challenge us today as well. So continue working on number 57, and please turn that in before you leave, number 57. After that, you have an assignment from yesterday to finish for Monday. And so those problems included, and this is on the calendar, and this is what was assigned yesterday, numbers 19 through 20, 23 through 26, 28, and 32. And these, again, are due on Monday. And there is a 64.9% chance that I'll do a homework check on those. So again, even if you get stuck on those problems, I expect that you show evidence of significant progress on those. So looking here at one particular example, this is number 24. And in number 24, you have a 20-gram ball of clay traveling east initially at 3 meters per second, collides with a 30-gram ball of clay traveling north at 2 meters per second. Then you're trying to find what the speed and direction are of the resulting 50-gram ball of clay. So this is a perfectly inelastic collision because once this lump meets up with this one, they collide and form one ball of clay with mass of 50 grams, and then head off in this direction toward the arrow that's drawn, the vector that's drawn on there. And so you're going to do the same sort of thing, or very similar to what we've done before, except for now we're dealing in 2 dimensions. So momentum initially in the x direction is going to equal momentum finally in the x direction. Same thing with the y direction. Momentum initially in the y direction is going to equal momentum finally in the y direction. Conservation of momentum in each particular direction. And so for each of these, you can figure out, okay, what is the, let's just focus here on the x direction. So the x direction initially, before the collision, where is the momentum? Well, this mass over here, the 20-gram mass of clay, has horizontal momentum, but the 30-gram one does not. And so would have mass 1 times velocity 1 plus, and this is all in the x direction, velocity 1 in the x direction, which it all is, plus mass 2 times velocity 2 in the x direction. And let's call this, well, this is mass 1 and this is mass 2 over here. And velocity in the x direction of mass 2 is 0. So this whole term is 0 because all of the initial momentum is in the y direction for that 30 gram mass. And that must equal what the x component of momentum is after the collision. So after the collision, we have only one particle, and it has a mass of 50 grams, or 0.05 kilograms, and then has some component of velocity, and this would be only the velocity in the x direction finally. So you're able to set this equation up, and you can do a similar thing in the y direction, and then solve, and you should get 1.7 meters per second and an angle 45 degrees north of east for that one. So work on that as well. Work that through. Last hint I'm going to give is for number 32. And for this is where we're starting to introduce a little more calculus now that the Calc 1 folks have talked about derivatives. And you're given an equation for momentum that's a function of time, and you're asked to find a force equation with respect to time as a function of time. And for this is again number 32. All you need to remember is that the force as a function of time is equal to the derivative of momentum with respect to t, so with respect to time. And so if you apply this, you should be able to easily find the derivative of the function that you're given in order to solve for that. So number 32 should be pretty fast and easy. All right, that's all I'm going to say. Hope you have a great weekend, and I'll see you on Monday with your problems done.